So now we're going to do some exercises, some problems that involve the laws of logarithms. And I recopied the three laws here at the top of this sheet. The log of the product is the sum of the logs. Log of a quotient is the difference of the logs. Log of a number to a power is the power times the log of the number. And I also wrote down a few other properties that we discussed earlier that come up every so often, and I like having this list all together. They're the three main laws, but there are these other properties we use too, especially the log to any base of 1 is 0. That can be a great help to simplifying. So let's go ahead and start doing some of these problems. And so we're going to start out by expanding each logarithm as much as possible. Number 1 is log base 2 of 3x times 5y. So we're trying to identify a form from one of the main laws. And I think you can see, I wrote some of these on index cards here. This problem is really all about log of a product. On my index cards, by the way, I didn't write the base b. I just have to remember that these laws apply to any base, and the base has to be the same in each log. It's a little simpler to write the laws down without all those little b's all over the place. So we're going to apply this law number 1 to this problem. We can say this log is log base 2 of 3x plus log base 2 of 5y. And I can actually keep going because 3x is 3 times x. That's another product. 5y is 5 times y. Each of these logs can be taken apart as sum of logs. Log base 2 of 3 plus log base 2 of x plus log base 2 of 5 plus log base 2 of y. And that's what we mean by expanding as much as possible. We've got 4 separate logs being added together there. Okay, let's go on to number 2. ln of 16. Now ln is the natural log. That's log base e. We can think of 16 as a product, right? One way I could think of it is as 4 times 4. And so that allows me to apply my first law again to this situation. Ln of 4 times 4 is ln of 4 plus ln of 4. And sort of similar to what we just did, each of these 4's is 2 times 2. So I have ln of 2 times 2 plus ln of 2 times 2. So these can be taken apart into ln2 plus ln2 plus another ln2 plus another ln2. And I guess I don't mind if you leave the answer this way, but it does look a little bit silly to have those 4 ln2's added together. You could just combine those as like terms. You have 4 ln2's. 4 times ln2 is a more succinct way to write that answer. So either one's okay, but I kind of like 4 ln2. Now there's another way we could have looked at this problem. We could have thought of 16 in a different way, because 16 is 2 times 2 times 2 times 2. It's 2 to the 4th power. If we had just written it as 2 to the 4th, we could have proceeded by applying the third law that has to do with the number raised to a power. the log of a number raised to a power is that power times the log of the number. So ln of 2 to the 4th is just that power 4 times ln of 2, the number inside. Notice that we get the same result as we did there, and it's a little faster. So sometimes there's different laws can be applied to the same problem. Maybe you'll save a little bit of trouble taking one route instead of another, but they both end up in the same place. Okay, number 3, I see log of 1 over x to the k. So I have log of a quotient, or a fraction, log of one quantity over another. That's going to be the log of the first minus the log of the second. So this is log of 1 minus log of x to the k here, where I have no base indicated, so it's understood that the base is base 10. And now, here is a good example where I see log of 1. What I want to do is apply the first of those other properties in my list, and this is the one that will come up most often, where log to any base of 1 is 0. We want to remember that we can always simplify log of 1 to 0 whenever it occurs. And then here I'm going to apply my log base to a power property and bring that power k out in front as a factor. So I get minus k times log of x k. And so all I'm left with is minus k times log x. Okay, let's go on to some more. So we got a few more of these. And we're going to continue to expand these as much as possible. I have log of x squared y cubed over z to the 4th. So I see log of a fraction. Now normally, if you see a combination of multiplication and division, you're only going to apply one law at a time. So I'm going to start out applying the second law. So I have log of x squared y cubed minus log of z to the 4th. Log of the numerator minus log of the denominator. Now this first log I can take apart since I have log of a product. That's going to be log of x squared plus log of y cubed minus log of z to the 4th. I just recopy for now. And now in each one of those terms I have an application of the third law. In each case I'm going to bring that power out in front as a factor. So my log of x squared becomes 2 log x plus I get 3 log y minus 4 log z, and that's it. So we're intentionally spreading these out into a big mess if we can, expanding as much as possible. Number 5. What's new in number 5 is that we have a square root sign. Now, in order to work with the square root sign here, we got to interpret this as an exponent. We can rewrite this problem as ln of, I'm going to add another grouping here, x times x plus 1 in those square brackets. That's to the 1/2 power. So I'm thinking of that square root sign as a 1/2 power exponent, because then I can apply my third law and bring that exponent out in front. And what I will have is 1/2 ln of x times x plus 1. And I can continue to expand by applying the first law because I have a product inside the parentheses. So I have 1/2 ln of x plus ln of x plus 1. And now, the way it's written right now, it's incorrect. So here, I have to realize that that 1/2 times in front applies to both of these terms. I either need to write grouping, or I need to distribute. If I want to expand as much as possible, I could distribute the 1/2 times each of those terms. And now, can I go further with this? Can I take apart the ln of x plus 1? And we can't. This is as far as we can expand. So the tricky part with this sometimes is trying to do something that's not allowed. Nowhere do we have a property where we have ln of a sum being taken apart into two separate logs. So this is not equal to like ln of x plus ln of 1. That's a real common kind of mistake. It's not equal. So watch out for that. You can't do that kind of simplification. Ln of a plus b can't be expanded ever, or log to any base of a sum. So that's as far as we can go in number 5. Let's look at number 6 now. It looks like we have log of a quotient again. So this is log base 2 of the numerator minus log base 2 of the denominator is yz. And now I have a product in that denominator. So I have log base 2 of x minus log base 2 of y plus log base 2 of z. Again, what I'm writing right here is incorrect. I have to fix this up because that minus sign will apply to both of these logs. I need grouping. And that means I need to distribute the minus sign. So this is actually log base 2 of x minus log base 2 of y minus log base 2 of z. And sometimes the way I think of this result is when I go back to the original problem, I just notice y and z were factors in the denominator. They both ended up with a minus sign in front. X was from the numerator, it ended up with a positive coefficient, or a positive 1 understood. So it kind of makes sense when you think about it, that the factors from the denominator will end up with minus signs. If you forget to distribute the minus sign, you forget the grouping, it's easy to accidentally leave a plus sign in front of the log base 2 of z, which is wrong. Okay? So we've got to watch out for that. So this is important. All right, so let's keep going. Got a few more problems we're going to do. In fact, now we're going to start doing a slightly different kind of problem. We're going to take these logs and condense them back together. So it's sort of like we're going to apply the properties in reverse. In fact, we're going to start out applying the second law of logarithms in reverse. We're going to start with the right-hand side and go back to the left-hand side. Now we can only work with 2 at a time, so we'll work with these first 2 logs, and I can say log base b of 3 minus log base b of 5 is log base b of 3 over 5 minus log base b of 2. And now I can apply, working backwards through the second law again, I can combine these two logs that I have now. And now I'm ending up with fractions of fractions, and what I would write here is log base b of, I wouldn't try to write a fraction with everything in it, I would write division. That's going to be log base b of 3/5 divided by 2, which is the same as divided by 2 over 1. So when I carry out that fraction division, that's 3/5 times a half. I invert the second fraction and multiply. So I have log base b of 3, 5 times 2 is 10, 3/10. It's my final log when I get those combined. So I wrote the first application of law 2 as a fraction, but when I applied it again, I wrote the division sign because I had to think through the division steps there of dividing by 2 to get my answer written in the right form. Number 2, now we want to apply law 2 backwards again, but to apply law 2 backwards, I can't have other numbers involved as coefficients in front of these logs. So what I really have to start with here is a backwards application of law 3 to the second term in this expression. So I'm going to leave the ln of x alone for now, and I'm actually going to take the 2/3 back up into the exponent of this base x, so it's going to be x to the 2/3 inside that second log. And now I can combine these two into ln of x over x to the 2/3. And that's, we combined into a single log, but that exponential expression inside can be simplified because that x inside is x to the first, which we can think of as x to the 3/3 power here. 3/3 minus 2/3 is 1/3, so all this is equal to ln of x to the 1/3 power just by simplifying exponents. And here we have another number 3, so we'll start out with the first two. That's kind of similar to number 1, right? We got log of x over y minus 3 log of w. Now that 3 has to be taken back inside as an exponent before I can combine the third log with the earlier one. So that's log of w to the third. And this is another good comparison to number 1, because I want to apply the second law again, so I'm just going to leave x over y as a fraction, but write divided by w cubed. That's like divided by w cubed over 1, which is log of x over y times 1 over w cubed. That w cubed will end up in the denominator, and I get log of x over y w cubed. And there's my single log from that one. Working backwards through this process again, note that it's kind of like the negative terms give me factors for the denominator. Positive terms will give me factors for the numerator. Okay, a little bit more. Run this through here. And a couple more combine into a single log. So once again, we got to start out by bringing these numbers in front, factors in front, up into the power. So the 1/2 will have to be brought up to the power. The 5 will have to be brought up to a power there. Let's see, we have ln of x to the 4th to the 1/2 power plus ln of just x to the 5th in my second one. I want to simplify this ln of x to the 4th to the 1/2. We know, write this on the side, x to the 4th to the 1/2 is equal to x to the 4/2, which is equal to x squared. So that mess is just going to simplify to ln of x squared plus ln of x to the 5th. And now I can multiply them together, a backwards application of law 1. That will be x squared times x to the 5th, which is ln of x to the 7th. And there's my combined into one logarithm, ln of x to the 7th. And finally, number 5. This, it's not really, there's not much we can do here, and it's more like a lesson in the fact that there's not much we can do. We cannot take apart addition inside parentheses, but we can combine these into a single log by a backwards application of law 2, and we'll get 2x plus 1 over 2x minus 1 inside parentheses, and there's actually nothing else we can do with this. We can't cancel 2's. 2's are not factors of the numerator or denominator. We can't simplify that fraction on the inside. That's basically it. It's more like a exercise in resisting temptation and not trying to do more than you actually can do. All right, so this has been a long video, but we're going to do little calculator exercise yet just to finish up. And this is a really important kind of exercise where we're going to convert, really the goal here is we want to find actual decimal values for log base 2 of 5. Let's just look at number 1 first of all, log base 2 of 5. And a calculator doesn't, most calculators do not have log base 2 buttons. Here's my scientific calculator. I have an LOG button and I have an LN, but I don't have log base 2. And it turns out that a log to any base can be converted to either ln or log, but either natural or common logs. Here we're just going to use natural logs, so we're going to use ln. And the textbook has a formula to use. I don't want to give you a formula. I want to give you a process. So here's the process. So what we're going to do is we're going to convert this to ln form, and then we're going to be able to use our calculators to evaluate it. To get started, though, I have to let x equal to log base 2 of 5. So I have to let this thing be equal to x, because then I can convert to exponential. Two to the x power is 5. That's the exponential form of that. I couldn't write that down without x having an x here or some variable equal to this quantity. And then we're going to take, what we say is we take ln of both sides. We're going to take the natural logarithm of both sides. So ln of 2 to the x is ln of 5. So we take ln of both sides of that equation, and then we're going to apply our third law of exponents and rewrite the left-hand side, because that x as a power can be brought out in front as a factor. X times ln 2 equals ln 5. And finally, we're going to divide both sides by ln of 2. So x is equal to ln of 5 over ln of 2 when we divide. So remember, we wanted this guy to begin with. We set it equal to x. So this ln 5 over ln 2 is actually equal to log base 2 of 5. So just in the chain of things here, log base 2 of 5 is equal to ln of 5 over ln of 2. That's what we've figured out. We introduced that variable x to allow us to convert to exponential form. Then we took ln of both sides, solve for x. And now what I'm going to do is I'm just going to use my calculator to get decimal values here for ln of 5 and ln of 2. And we have to round off because these are going to be infinite decimals. So I'm just, let's see on my calculator, 5 ln, that's all it takes, and I get a decimal. Rounding off to 5 places, I'm getting 1.60944. I'm also going to compute 2 ln, and I get 0.69315. And then I'm going to divide those two. And when I divide, I get 2.32192. And that's what we're after here. So, and again, just that's equal to log base 2 of 5, 2.32192. So this red kind of sums up our calculation without all the steps written in. We started with log base 2 of 5. It's equal to this fraction in natural logs, which is equal to that decimal. And it's fine with me if you can push calculator buttons and not have to write down decimals along the way. That's fine. It's really only that final result that we are after. So I want to do this one more time. We're going to compute log base 13 of 0.2. And so we'll start out by letting x equal log base 13 of 0.2. 13 to the x is 0.2. We're writing the exponential form. And now we're going to take ln of both sides. Ln of 13 to the x is ln of 0.2. I'm going to rewrite now, applying that exponential third law of logarithms. X ln of 13 is ln of 0.2. Solve for x by dividing both sides by ln of 13. X is equal to ln of 0.2 over ln of 13. And now just I need decimal values to get my final decimal answer for this. And I went ahead and did that already here. ln of 0.2 is actually negative 1.60944, rounded off. So that's a negative value of that log. Divided by ln of 13 is 2.56495. And when I divide those out, I got negative 0.62747. So it's a negative number that is equal to log base 13 of 0.2 has that decimal value. We got it by going through this process and using natural log and natural log buttons on our calculator. So that's the end of the problems for this section.